is the actual calculus for how to deal with multivariable functions. In particular, we'll start with the derivative. So let me actually start here on Mathematica instead of on the thing. Let's see. Oops, that's not the right button. I want Mathematica. Oops. Okay, so let me just pick a sort of random multivariable function and define that. And okay, so I get this surface here. Okay, whatever. It's sort of like a, it'd be like a parabola, but like imagine if you made like on a rain gutter in the shape of a parabola, right? And you'd want it to slope slightly so that water would flow down it or something like that, right? Okay, so anyway, that's our shape. Um, and what we want to do is we want to kind of think about, and let me also, while we're at it, let's do the contour plot um, and look at sort of the topographical map for this thing. Right, and it would look like this. Okay, so what are we seeing there? We're seeing that as we move, say, downwards, which is in the y direction, what's true about the height of our function? Yeah, it also goes down, and then we've got sort of this parabola-y looking thing going on. So, so it's like a little rain trough or something. The contour plot. So this is like the topographical map version, right? So it's like we're looking down on the object. Um, no, it well, and the reason is that because of the color coding, right? So things that have lower z values are shaded darker, and things that have higher z values are shaded lighter. And so if we looked at this from the bottom or from the top, it would actually be the same thing because it's the shading takes that into account. Um, but I think it's maybe more natural to think about it looking at it from top down because that's, well, I mean, that's how we make maps, right? That's sort of the perspective that we use. Um, and actually, okay, I take that back. If you looked at it from the bottom up, then uh, up would be this way and down would be that way. But if you looked at it from the top down, up would be that way, right? So it would reverse one of the axes because your point of view is different. But yeah, so we're basically looking at it from the positive z-axis looking down. Okay, great. Um, now in this case, in either the surface or the top of, I mean the this view, if you walk along this direction, okay, what do you think is true about the slope that you're walking along? Just from the picture. Looks constant, okay? Whereas if you were to walk, say, this way, you'd be going down into the trough and then you'd hit the sort of middle of the trough and then you'd start going back up again. Okay. All right. And if you walk at some weird angle, then well, who knows, right? But importantly, it's going to be some combination of those two things. So what we can do is we can look at what's the slope, if you will, in one direction, and what's the slope in the other. Now, in this case, what's the slope in the y direction? It's constant, okay? And it doesn't matter where on this surface you are, it's the same constant too, okay? Does that kind of make sense? Like if I look at it edgewise? If the slope is well 1, but well, I mean we can kind of well, okay, good question, but like let's say from this point, so right here, that where my mouse cursor is at z equals 0, and what's at the other end of it? Uh, well, okay, yeah, good question, right? So, if I go from where my mouse cursor is now to here, we have gone up 2 units, but how far over have we gone? Also 2 units. Yeah. Okay, so the rise over run computation we would make would be 2 over 2 is 1, and so that edge looks like it has slope 1. Yeah. Okay. And it actually doesn't matter where along the trough that I do this, the rise and the run amounts would be the same. Okay. And that's only because of the particular function I picked. If I change the function up, then of course who knows. But uh, right, that's what I chose. Okay. So what I'd like to do then is let's take first off, let's pick a point. Okay, and it could be any point on this surface. For just sake of demonstration, I'm going to choose the origin. Okay, 0, comma 0. All right, that's nothing special about it. It's just an easier point to pick. And what I'm going to do is, and hopefully this will work right. Um, of course not. Okay, why didn't that work? Um, oh, right. It's because I didn't specify 2 coordinates. Okay, hang on. Let me think for a moment. If I want x to be constant at 0, then I want that's what I wanted. Okay, excellent. All right, so I want to make, let me name these plots and hide them. And then I'm going to name this one P3. And then what I want to do is show P1 and P3. Okay. All right, so what I've done is I've drawn in blue basically at so what did I do? I drew a the surface, if you will, or I did it parametrically, thinking of I want x to be fixed at 0. Okay, so the x coordinates, I'm going to graph a collection of points whose x coordinate is 0, whose y coordinate is y, could be whatever, and whose z coordinate is given by the function. But what's the x coordinate? 0. Okay, so the height of the thing will be f of 0 comma y, and the y coordinate will be whatever, and the x coordinate will be constant at 0. Okay, so this is just like one of those straight lines or edges, if you will. Yeah, Cole. So in this situation, is are x and y on the front page, like the front little bar, and then these like that? No, no. This is x, this is y, and this is z. Okay. Now, if I rotate the figure, then the where Mathematica puts the labeling for the axes might change, but yeah, the z direction is the vertic running up and down the screen. The no, it's yeah, okay. Now I should mention, by the way, that uh, that's the coordinate system for the within the picture. Um, if you do graphics programming on a computer, It's actually exactly what you said. So this is really just drives me crazy when I'm doing graphics programming. But the x-axis on the screen, so first off, we've got to put the origin somewhere. And the convention is that the origin in graphics program goes at the top left. Okay. And the x-axis runs horizontally from the top left. Okay, that makes sense. Okay, but then the y-axis runs down, not up. And the z-axis, when you're doing 3D programming, is basically how far into the screen or out of the screen you are. It does make sense, but it's also irritating, right? I'd rather it be the same as math. Okay. Yeah. Okay. Now, what makes that particularly annoying is that that is a left-handed coordinate system, and math uses a right-handed coordinate system, right? So it's not like you can't convert between them. It's not that hard. It's just annoying because you have to. Anyway, so but in our plot, no, the z-axis is running vertically by default, and I mean unless I like rotate it all crazy, but yeah. Okay, so what I want to do then is I want to do the same thing, but instead of holding x constant at 0, I'm going to hold y constant at 0. And there's nothing special about uh, 0. That's just the middle of my graph, so I'm using that as an example point. And I'm going to put this one in, instead of blue, I'm going to put this one in red, and then I need to show P4. Okay, so I get the same thing. I get this red parabola there. Okay, and here's the other thing I can do. Okay, the blue curve and the red curve are within a plane, right? So they have either constant x or constant y, as the case may be. Okay, what that means though is that they are really describable by a single variable function. Okay, so I can talk about what's the derivative of each of them. Okay, so what's the derivative of the blue function with respect to y? 1. Okay, and in that case, it was easy to do that because it was a straight line, right? And we just figured out its slope. Okay, but what about the parabola part, this red thing? What's the derivative of it with respect to x? 2x. Okay, does that make sense? All right, now let's think about why that makes sense. Well, first off, if I look at the function f of x comma 0, it's x squared. Well, what's the derivative of that with respect to x? Last time I checked, it'd be 2x, right? Okay, so what we've done is we basically said, okay, if you pick a point, then it makes sense to talk about the derivative in the x direction or the y direction. Okay, and if I did the same thing with holding x constant and letting y be the variable, then that would be the function this, and what's it? F of 0 comma y is y. What's the derivative of it? Which is shock. That's what we said when we did this graphically. The slope of the blue line. Yeah. Okay. And the derivative with respect to x would be the slope of the red parabola. Well, that makes sense. Yeah? Okay. So what we defined here is what we call partial derivatives. Okay. All right. So now we need to go back over to the iPad and write all the details out here. So, and I don't have a preset for that. So, we want the Elgato. Okay. All right. So what we've defined here are what we'll call partial derivatives. okay? And the way that we define those is as follows. So first off, if we hold so for all of this, we've got some function of, say, two variables, okay? Um, I want F here. Okay, so if I hold one of the variables constant and let the other one vary, and then do what I just did, okay, then we could talk about the derivative of it with respect to x if I hold y constant, and y if I hold x constant, right? So it's sort of which one. Uh, okay, and the way that we write this is it's df dx, but the little d looks funny. Okay, so it's kind of like this fish hook looking symbol. It's not the letter D. Okay, so does that, you guys see it? Make sense? Um, okay, and that's just the symbol that we use. And the reason that we use that symbol is because um, it looks different than the letter D, and so this sort of reminds us that we're not doing a derivative like in Calc 1, we're doing sort of the multivariable version of it, okay? And now, how is this defined formally? Um, del f del x at a point x naught comma y naught is defined to be the limit as h approaches 0 of f of uh, x naught plus h comma y naught minus f of x naught y naught all over h. Okay, so what have I done there? Well, doesn't that look like the definition of the derivative from Calc 1? Okay, but what kind of function am I dealing with here? It's multivariable, okay, so it depends on two coordinates instead of one. And what I've done is I've let the x coordinate vary and the y coordinate stay constant at the value y naught, okay? And so if I do, what am I doing there? I'm doing a rise over run computation, right? That's what that fraction is. And but it's only in one axis. It's along the x-axis that I'm doing the rise over the run computation. Okay. Similarly, which is a dangerous word in math, the del or yeah. So um, it's really d. For some reason, I always just say del. Right. So people will say this df dy. I like to say del f dy, del f del y, because then it's clear to you that um, um, that's not the same as the d symbol, and I really mean a multivariable concept. Um, yeah. So I just say del. It's not proper, but yeah, it is what it is. Okay. Okay. And so similarly, I could define the partial derivative in the other direction by holding x constant and letting y vary. right? And again, I'm doing a rise over run computation. It's just in the other axis, okay? And what's nice about this is if I had 17 variables, I could talk about the derivatives with respect to each of those 17 variables by doing something basically like this. And now, obviously, 17 variables, I mean, that's a ridiculous number, and I just pulled that out of thin air, but yeah. Well, okay. So Cole's question was how many more variables or dimensions are there? Well, okay. Do you mean in physics? Hmm. Yeah, three dimensions. Well, just any unknown quantity, right? So, okay. So, like, the question fundamentally that you're asking is, um, how do you visualize a situation with 17 variables, right? I don't know. I don't know how to do it with four, right? I mean, now you could, if you wanted, think of, okay, if you've got four variables, you could have an X, a Y, a Z, and then you could make the fourth one like a T for time, and like it'd be like your object, your surface or whatever, would, depending on what T is, would look different. Okay, but good luck imagining that. It's hard. And uh yeah, it's that's hard. Okay. Um and so if you kick it up to like 17 or whatever, right? Even double good luck. You lose the ability to visualize it because we live in a three-dimensional world and we visualize things in three dimensions, right? I mean, now that said, in a physics context, what do we live in? Really, a four-dimensional world, right? There are three spatial dimensions, right? X, Y, Z kind of thing, and then there's a fourth time dimension, and space-time is weird and curved and it's complicated, right? And for that, I invite you to become a physics major. Yeah, well, that's not a bad thing, right? To contemplate life. It depends on his speed, but younger. Yeah, that's called the twin paradox. So, and it's because uh, time or your perception of it doesn't change, but your time versus my time is the same. Okay, but if I start going like significant fractions of the speed of light, the way I perceive my time is the same, but my time slows down with respect to your time. And so I would, if I went, if I took a year and traveled at half the speed of light for that year and just did like a grand old tour of uh, the solar system, I would come back and I would be younger than, I would have aged less than you would have. Yes. Why do you think it took until Einstein in 1905 to even begin to start to figure this stuff out? I mean, part of it was that we didn't really have the math to describe it well until the 19th century, but yeah. So anyway, okay. So yeah. So visualizing this stuff for more than two variables or three dimensions is hard. Um, but mathematically, we don't have to visualize it, right? It's just symbols on a piece of paper. Um, how you visualize it is you being a human and having a problem, but that's not math's problem. That's your problem. Okay. Okay. So if we get back to what we did, let's take the function, the particular example that we were looking at. Right. I just picked x squared plus y. Okay, so accordingly, del f del x would be the limit as h goes to 0 of f of um, x, sorry, x plus h, dang it, comma, y minus f of x comma y all over h. Okay, so that's what I've done, right? This looks just like when we did Calc 1 and defined the derivative. We started setting up difference quotients like that. Same thing. Okay, it's just that it's multivariable this time. All right, so what is f of x plus h comma y? Well, it would be x plus h squared plus y minus x squared plus y all over h. Okay, and if I FOIL this stuff out, right, that looks familiar. Yeah, just foiling. Okay, does that make sense? Yeah. All right, so now that I've set all that up, what cancels? Lots of stuff. The x squared cancels, the y cancels, and so I have h squared plus 2xh over h. And what do I get in this case? If I cancel an h, I'd get the limit as h goes to 0 of h plus 2x, which is 2x, right? Because x doesn't depend on h. Okay, does that kind of make sense? Now, one thing to note is in this particular case, and this is only because of the example function I chose, um, what happened with the y's? They all disappeared. Okay, I could come up with the function though where that didn't happen, and that our answer could still have both x's and y's in it. It didn't in this example, but it could in theory. Okay. Um, so don't think that the derivative with respect to x always only depends on x. It could depend on y also. Okay. Our example didn't, but that's just our example. Okay. Is that okay? How is that ever going to happen if the second part of our thing is just y minus y? Because, well, like, let's say, for example, I picked the function x squared y instead of x squared plus y. Okay, so let's do that example. Right, so do you guys see what Will's question is? It's like, well, how is that going to happen if I just turn around and subtract something, right? Well, all right, so let's do that example. So let me just say g of xy equals x squared y. Okay, for example. Okay, so del f del x would be the limit as h goes to 0 of g of x plus h comma y minus g of xy all over h, right? So that's just setting up the difference quotient. Yes? Okay. All right, so now what is g of x comma, or x plus h comma y? It'd be x plus h squared y minus x squared y all over h, right? And the y's don't just magically cancel in this case like they did before. If we multiply all this crap out, then what are we going to get? Well, we get x squared plus 2xh plus h squared times y minus x squared y. And so some of the stuff is going to cancel, sure, right? Because this would be x squared y plus 2xhy plus h squared y minus x squared y all over h. And so that leaves us with what? 2xhy plus h squared y over h. Cancel an h. And we get voila. Okay. Does that kind of make sense? Okay. So if you pick a specific point, then this tells you the slope in the x direction at that point. So example, well, let me not do 1, 1, just because let me pick two different values. Okay, so it means that at that particular point, your slope in the x direction is 4. Yes. Yes. That just means plug in x equals 1, y equals 2 to the thing. Huh? Yeah, it doesn't, it's not like the bar that we write with integrals, um, where there's a top number and a bottom number. This just means take the thing, del f del x, which is 2xy in this case, and plug 1 in for x and 2 in for y, and then whatever you get is whatever you get. Okay. Yeah. Okay, is that all right? So in this case, we got 4, and so what that would mean is if I graphed this surface, so let's do that. Um, okay, so let's bounce back over to Mathematica. Okay, so let me do it. G of xy equals x squared y, and then I want to plot G. I picked the point 1 comma 2, so what I'm going to do is I'm going to let x go from 0 to 2 and y go from 1 to 3 for the part of the graph I'm going to look at, so that 1 comma 2 is at the middle of the graph. Is that okay? And what do I get? I get this warbled looking thing, okay? And let's do like we did before, and let me draw, okay, so what I'm going to do is I've already used P, so I'm going to call this one Q, dang it. And then these guys I'm going to call Q1 and Q2, and then I just need to define them to be G, and then what was the point I picked? 1 comma 2. And then Y I was going to let go from 1 to 3, and X from 0 to 2. Was that correct? Yeah. And then I want to show Q1, Q3, and Q4 to layer these guys together. Okay, so same sort of idea. What's the slope in the X direction? Well, it depends on where we are in the Y direction too, right? Because the slope, if I'm here, is 0, and the slope, if I'm up here, is along the red curve, is something else. Definitely not 0. Okay, and what is the slope at the point that I've computed when x is 1 and y is 2? We got 4 by doing this by hand, okay? And so if I look at that red curve, let me plot that in a single dimension. Oops, where am I? Here. Okay, so I want to do g of which one are we doing? Are we letting X be fixed or Y be fixed? Red is letting Y be fixed. Okay, so I would do G of X comma 2 for X ranging from 0 to 2. And I get this, right? So that red, in fact, let me change this to make the colors match. Okay. Um, what we're looking at is basically if I pluck that red curve out of my three-dimensional figure, I can put it onto a piece of paper, and that's what it would look like, right? Is this a two-dimensional plot? And at the point x equals 1, okay, which would be right here, what's the slope of the tangent line there? Okay, now the scale here is misleading. Okay, what does it look like the slope is? Maybe one-ish. Okay, just visually, but this is deceptive because look at the scales. Like look at the scale on the y-axis, right? Okay, so what I can do to sort of fix this is I can do, okay, and so this makes it a 1-to-1 aspect ratio so that, um, actually, no, I didn't want aspect ratio that. I wanted 4. This is more accurate, right? And so at this point right here, what's the slope is what we're asking. Does 4 seem like a reasonable number now that I've drawn it with sort of correct aspect ratio? Huh? Yeah, seems reasonable. Okay, so let me be clear. The slope of that tangent line is 4. How it's not dependent on how I draw my picture. Okay, um, but making the picture look like what uh, is true numerically is certainly helpful. Yeah. Okay, so does that kind of make sense, Will? Yeah. Okay. That it could depend on the slope could depend on where you are in both coordinates. Okay. Okay. So let's go back over to um, the iPad for a moment. Oops. There we go. Okay. So what we've defined here is the partial derivatives del f del x and del f del y. And we could do this if there were any number of variables, but we'll just stick with the case of 2 because that means we can draw good pictures. Um, now, there's a couple of things. So think back to Calc 1, right? When you guys learned the definition of the derivative, and then what happened? You're like, oh man, this sucks to do the definition of the derivative to compute that the derivative of x squared is 2x. Well, okay, you didn't want to do it that way. You did it first, but then what happened? You learned the power rule. And you're like, oh, this is so much easier. I can just bring the exponent down and so on, right? Huh? Yeah. If you don't know what the power rule is, then at this point in MAT112, you're going to have a bad time, right? If you pizza when you should have French fried, you're going to have a bad time. Okay. South Park. Um, there's an episode where all the families they go to a ski resort in Colorado, and the parents get trapped in like timeshare presentations the whole time, and so they don't actually get to go skiing, but the kids do. And so the kids are with like a ski instructor, and he's talking about like if you if you put your skis parallel, then that's French frying, and you would go faster. And if you put your skis so that they're point making a triangle, then that's pizzaing and you would slow down, right? So skiing is the art of going downhill, adjusting the angle of your skis to either speed up or slow down at the appropriate time. And so he's like, if you pizza when you should have French fried, you're gonna have a bad time. Okay. Well, not quite the okay, but yeah, that's the idea. Okay. So you could do all of this with limits, okay, but it would be painful. And the good thing is that all of the rules, the tricks, power rule, chain rule, quotient rule, uh, product rule, those are still on the table, but we have to kind of do them in a multivariable context. Okay, so let's take, for example, the function that I was using, right? So we had g of xy was x squared y, and del, or sorry, not del f, del g would be what? Well, what did we say it was after we computed it with the limits? Or I'm sorry, I wanted x, not y. Okay, we got 2xy by doing a limit computation on the last page. How could we have gotten 2xy without doing the limit computation? Well, so when I see x squared y, I'm going to say, all right, is y a variable and x a variable? Yeah, they're both variables. Okay. What I want you to do is I want you to pretend for right this instant that y is actually not a variable but a constant. Right? So it's like the number pi or 7. If this were x squared times 7, what would the derivative be? Well, it's not gone because it's multiplied, but it'd be 14x, right? Okay, so what's the derivative of x squared times some number? It's 2x times that number. Yes? Well, what's the number? In this case, it's y, right? So if I think of if it's x squared times 7, what's the derivative? 2x times 7. If it's x squared times 36, what's the derivative? 2x times 36. So if it's x squared times y, what's the derivative? 2x times y. Well, that was easy. Okay, so what does this mean? Do we have to do the limit computations all the time? No, fortunately, because that sucks, right? Okay, but the chain rule and all of that still applies. Okay, so um, what do we got to do? Well, well, and while we're at it, what's del f del y in this case? Well, now the way I want to think of this is it's my function is x squared. Oh, there it goes. Okay, I don't know why that happened, but okay. So if I'm taking the derivative of x squared y and I pretend that x is a constant, then I'm taking the derivative of some fancy number times. I would just get del f del y is x squared in this case. And it's coincidence that that one doesn't depend on y also. It's just because of the example I picked. Okay, so let's do another example. Oops, I don't need a second equals there. the stuff times the derivative of the stuff. Okay, so this part is the chain rule, like from Calc 1. Okay, now we're not done yet, but that's sort of the first step. Do you mind if I? Well, let's take two. Yeah. Yeah, I am parched, is putting it mildly. Um, Sparks yesterday did not agree with me, so I had a rough night. Um, all right, so the chain rule says we need to multiply by the derivative of the inside. Okay, now we need to figure out what that is. Okay, but when I do this, what is the derivative of xy with respect to x? It's just y. Okay, so the irony of this is that by introducing more variables, it actually gets easier to take the derivatives in many cases. Because if you were in Calc 1 and you looked at x times y, you might think, oh, I'm supposed to do the product rule here. Okay, but I don't have to because I'm thinking of, if I'm doing this with respect to x, y is a constant. And so x times y is really just x times some number, right? And so I don't have to do the product rule in this case, which is nice, right? It simplifies things a bit. Okay, now this isn't to say that you never have to do the product rule. It's just that you don't have to do it as much as you might otherwise think you do. Okay. Um, okay, um, so in this case, we would get cos xy times y. All right, now, what's del h del y? Yes? Right. Okay, for basically the same reason. Okay. And it doesn't matter where you put the x or the y, right? Like, I prefer usually to put them out front of a cosine term, but yeah. Okay, good. Well, that's nice. Is that it's actually, in many cases, easier to do this partial derivative than it is to do a complete, like, Calc 1 style derivative. Okay. So the very last thing I want to do, and this will just be for right now real brief, and we'll talk about what this thing means later, um, is okay. So I'm going to define a new quantity called nabla f or del f. Okay, huh? No, it's not what you think it means. Nabla. Oh, okay. Well, it's not a variable. It's just a symbol. Okay. Now, um, be very careful to spell this correctly if you ever Google it, because it's Nabla, Nabla, and it's the name of like a harp, an ancient harp, right? So, imagine strings running vertically, and I'd hold it here and be like, bling, bling, right? Okay. But be very careful, because if you mistype it, you will find a very, very different website than you think. So be careful. Okay. All this means, though, is to take the two partial derivatives and put them together in a vector. The derivative with respect to x goes in the first coordinate, and the derivative with respect to y goes in the second coordinate. Okay, and this thing is called the gradient. Okay, so defining it's easy. Just take the two partial derivatives, throw them in a vector, done. That's it. Okay, what we can do with this thing, though, is really quite cool. And for that, you lamentably have to wait until next week. Okay? And you think like the Mathematica has been cool now? Just wait. Okay. All right. So have a fantastic weekend. Get some rest. Get some work done. And I'll see you guys on Monday.